Hi, I'm Dominik. Today I'd like to talk about some of the work I did during my PhD at the University of Oxford, where I was advised by Edith Elkind. Rather than go through the dissertation chapter by chapter or theorem by theorem, I thought it would be more fun to take a relatively informal approach, just discuss some of the main themes in the dissertation, talk about what has been said about them, both by others and by the work in the dissertation, and then sketch some of the main open problems that remain. The title of the dissertation is Fair Division of the Commons, a wordplay on the tragedy of the commons, a well-known collective action problem. By fair division of the commons, I mean the problem of a group of agents to decide how to use a common resource. So we have a group of agents, they have some common budget that they could use for very many different things, and they have different preferences about how to use the budget. They should come together, make a group decision, and we want to decide on this division of the budget between different users in a fair manner. So every group member should have approximately equal influence on the outcome. Now we're going to study this problem from the perspective of voting theory, also known as social choice theory. So we're looking for voting rules or voting mechanisms that take as input the preferences of the agents over the use of the budget and then output a particular division of the budget. So let me give you a specific example of a problem that came up a while ago. While I was in Oxford, I was a member of Balliol College, and the graduate students there have a common room. And in that room there's a big table with newspapers and magazines. And we have an annual budget of around £2,000 for those subscriptions, and once a year a committee member sends around an email to everyone with a form, a survey, or a vote really, where you can indicate which newspapers and magazines you would like to the common room to subscribe to. And so in 2018 there were 80 subscription possibilities, 80 options and periodicals in that list, and you were allowed to tick as many of them as you like. This is called approval voting. So for instance, you might want to subscribe to The Economist, you might want to subscribe to The Guardian, you might want to subscribe to, I don't know, Nature, or some things that are more targeted to you specifically, such as if you're German, you might choose German magazines or something like that. Okay, and so once everyone's done that, you can then take all these votes together and then have to decide which ones you buy given those votes. How do you do that? One obvious method, and the one we actually ended up using, is to order the periodicals by the number of votes they get, and then buy the most popular one. If there's a remaining budget, buy the next most popular one, and so on until you've exhausted the budget. And if you do that, in our case, this is what happened. So out of the 80 options, we only could afford 9 of them, the 9 most popular ones, like The Economist, The Guardian, and so on. And what's interesting about this selection is that most of the ones that we bought were pretty expensive. Right? So for instance, The Guardian is a daily newspaper. It costs almost £600 a year. The Financial Times costs over £600 a year. And so this is why we exhausted the budget pretty quickly. Now notice that if we had chosen not to include the Financial Times, then with those £600 we could have instead bought 20 monthly magazines that cost about £30 a year, such as like Private Eye or many other options. Now, which is the better choice? It's unclear, but maybe this is not the perfect voting rule, and we should select something that covers more people's interest. Now, I'm not certain what is the optimal voting rule, but we'll try to make some progress here. And why is this problem interesting? Well, this is a kind of toy example, but the exact same problem occurs in much higher stake scenarios. So one example is participatory budgeting, which is the same thing, but on the city level. So in participatory budgeting, a city government sets aside some fraction of their budget and lets residents vote over how the budget is used, what projects are being financed with it. This started in Latin America, but is now popular across the globe in many, many cities. In the US, the Stanford crowdsourced democracy team has pushed this very successfully, and they've built a participatory budgeting platform, which makes it easy for cities to run these projects, and you get these wonderful online ballots. So here's an example from Boston, where you can select where each voter can select up to 4 projects. So you might, for example, vote for a bike lane installation or renovating a park. You can see it's essentially the same problem, just with a couple more zeros in the costs. Now, and again, probably they will use a similar system of funding the most popular projects. Similarly, the biggest participatory budgeting project that's around is in Paris, where they spend more than 100 million euros every year based on this election. So there are 30 million euros for the entirety of Paris and 60 million euros split between the arrondissements. And this is a big deal in Paris. So here's a photo I took in September, where the ads in a subway station all tell you to please vote and make your voice heard. Now, and again, it's the same kind of trick. You are allowed to approve up to 4 different projects, and then they fund the most popular ones. There's a little complication there, where some projects are targeted towards working class areas, and there are lower bounds. So there's a constraint that says at least a certain part of the budget should be spent on working class areas. Okay, so let's have a look at data from Paris to see what this rule does. So I've made a list of all the projects that were around in the election in 2019. This is for the entirety of Paris. And these are the projects. This is the cost of each project, how many people voted for each. And the projects with a star here are those in working class areas. And now in the greedy column, you can see which projects actually won and were funded last year. And so this is just the most popular projects with some exceptions. And these exceptions come about because we have this constraint saying that working class areas should get at least something. Okay, there's also this optimal column, and I'll talk about that in a second. I want to show you a weird thing that can happen, analogous to what we saw with newspapers in Balliol College. So if we go to the 10th arrondissement and look at their local election, then here the most popular project is about putting solar panels on school rooftops. It costs almost 1 million euros and it got 3,000 votes, which is the highest number. So the greedy mechanism that they use immediately bought it and funded it. Now, if we go further down the list here, we see an interesting project here. What happened there is they closed one afternoon, they closed some city street and let children play there, had a party. And that was a great success. They want to repeat it, and for future iterations, they want to buy some picnic tables and chairs. And that will cost them 10,000 euros, and it got almost 1,000 votes. So if you look at the ratio of votes divided by 1,000 euros, there are 100 for this little project and only 3 for the big solar panel project. So that's a 33 difference in cost effectiveness, if you like, of these projects. But turns out that this cheap project was not selected by the voting rule used in Paris. Why? Well, the most popular projects, like our newspapers, are really expensive, and after buying them, no money was left to buy these good deals. And so that's unfortunate. What's an alternative rule that we could use? One is the optimal rule I alluded to, which works like this. We go through all possible combinations of projects, bundles of projects that we can afford and satisfy the working class area constraint. Look through all of them, and for each of them we compute the sum of votes that the projects in that bundle received. And then we just select the bundle that has the highest vote count like that. If we do that, we can see that many more of the cheap projects with fewer votes get elected, and that makes sense given the objective function we're maximizing, because if you fund lots of cheap projects, you probably rack up more total votes, right? And we can see that repeated in almost all the local elections where some of the expensive projects are skipped in favor of funding several cheaper projects. Which of these two rules is better? It's not completely clear. It depends a bit on what people mean when they vote for a project. Do they say, this project is worth its cost? Or do they just say, I like this project? Also, probably don't have enough information because we've only used the number of votes each project got. But we really want to know which projects are approved by the same people and which projects are approved by different people, so that we can be sure that no group of people is completely ignored by the procedure. We'll look at these kinds of cases in more detail later. There could be a different kind of strategy, right? In Balliol, we could have asked first, sort of, how many newspapers do you want? Like what fraction of the money should we spend on these expensive things? And then based on that decision, we could make more fine-grained decisions, like which newspapers, which magazines. Now, a similar idea is used in Chicago here in this example, where they ask their residents first, what fraction of the budget do you want to go towards street resurfacing? They have cold winters in Chicago, so they have to do that all the time. So you first say what fraction of the $1 million pot should go to that, and then after that's aggregated, there's a remainder of the budget, and that's spent for other projects that you can vote down below. Okay, so let's follow this idea of asking what percentage should go to newspapers or street resurfacing. And so we need to aggregate those numbers. Now, what method can we use to aggregate different people's favorite fraction? The first idea for this task is to just take the average, the mean. And that's a really good choice because it lies nicely in the middle of the numbers reported. It is fair, everyone has the same amount of influence on the position of the mean. It's very responsive to preferences. If anyone changes their mind, the mean goes to where they think it should go. But it has some problems as well because it's kind of too responsive to preferences. What do I mean? So suppose in this example where we had 10%, 19%, 40%, 70%, 5 voters who have different ideas on the fraction spent for newspapers, for instance. And if you're the 70% person, the current mean at 44% is too low, you think. It should be higher, we should spend more on newspapers. What you can do is you can lie and you can pretend you are really, really into newspapers and instead say something like, say 95% should go to newspapers, and then the mean has gone up from 44 to 49. It's still not at your perfect number of 70, but it's better. Right? And similarly, people who think it's too high should go a bit, should under-report, like everyone will exaggerate what they think. And so, while fair, the mean is not good if people are strategic. Okay, what can we do? Can we kind of avoid strategic behavior? Okay, so if the average is not good enough, the next best idea is the median. And the median is just take the middle value of the numbers that were said. So in this case, there are 5 people, so the third highest number that anyone said. Okay, so in this case, this is the 26 down here. Now this is looking good. So if you're the 80% person up here, you're pretty unhappy with the median. Can you pull it further up? Well, let's try. Well, that doesn't help. Exaggerating your opinion does not help under the median because the median just doesn't change. It's always the third highest value, so if you're higher than that and go even higher, the median doesn't change. Okay, so the other option, of course, would be to go lower. You have to go much lower, but that doesn't help either because once you cross the median, you can then pull it down further and go further away from your favorite of 80%. So that's no good. Okay, so now we found what's called strategy proof or truthful mechanism. That's great, it can't be manipulated, but there are some problems with the median. Consider, for instance, suppose of the 5 people we have, there are 3 people who are really into newspapers and 2 people who are more into magazines. So we have 3 high reports and 2 low reports. What does the median do? Well, it takes the third highest report, which is really high. So it goes with the majority opinion and completely ignores the minority opinion, which is unfair to the minority. Compare that to the mean that goes sort of 3/5 of the way towards the high values, but stays sort of close, like mixes in some of the opinions of low value people. Okay, so now we have one mechanism, the mean, that can be manipulated but is fair. And we have one mechanism, the median, that cannot be manipulated but is unfair. Can we combine these 2 properties? Okay, let's think about it. So, are there any other rules besides the median that cannot be manipulated? The answer is yes. So an example of such a rule would be just take the lowest number anyone ever said. Right? That you can't manipulate because if you're higher than that, you probably don't want to say something even lower than the lowest number. If you are at the lowest value, then you're perfectly happy, so you don't want to manipulate either. In general, we know actually the entire class of mechanisms that are not manipulable. Hervé Moulin characterized this class. And what it is essentially take the median, but only after we've added some extra fixed numbers into the mix. So for instance, in this example, suppose there were fake voters, which are called phantom voters, like 4 of them, and they all say 0. And if we then take the median of these phantom values, 0, and the 5 real values, what is it going to be? It's always going to be the lowest real value, right? So this alternative strategy proof rule is one of these generalized median rules, where we take the median of the real values together with some phantom fake values. Okay, so now we know the entire class of truthful rules. Is there any of them that is fair? The answer is kind of. Turns out that the optimal way to put these phantom values is to put them uniformly between 0 and 1. So you put them at 0, 20, 40, 60, 80, and 100%. And the resulting rule is reasonably fair. So there was an ICML paper that proved that the median with those uniform phantoms is never too far away from the mean. Here it's very close at 60 versus 59. And it makes sense, right? So there are 60% of the voters are sort of close to 100%, they are high. 40% of the voters are pretty close to 0, they are low, and so the uniform phantoms takes 60%. Cool, so that's nice, and that seems promising as a first step in our rule of first deciding what fraction of the budget should go to newspapers versus magazines, or street resurfacing versus other projects in Chicago. Now, here's a problem. What do we do if we have more categories? So suppose we actually want to split the periodicals into dailies, weeklies, and monthlies, rather than just dailies and non-dailies. Or maybe Chicago wants to ask what fraction should go to street resurfacing, what fraction should go to policing, and what's the remainder that should go to other projects. What can we do then? Well, the easiest idea would be to sort of multiply this picture, draw it 3 times for the 3 different categories, and just have in like the first bar put all the ideal values for dailies, for monthlies, and for weeklies. And then take the uniform phantom value, and that will be strategy proof again, and it will be as fair as the uniform phantoms are. But there's a problem. Here's the case where we do this. So now we have 3 agents here. Agent 1's favorite would be 100% on this purple project, 50-50 between purple and reddish for agent 2, and agent 3 is all in for green. Okay, and then we take uniform phantoms on each of these 3 projects independently. And what happens? Well, it says we should spend 50% on purple, a third on red, and a third on green. Right, but 50 plus 33 plus 33 is more than 100. We've overshot. We don't have that budget left. Right, and uniform will do that. Like taking uniform phantoms in each coordinate separately will always overshoot. So if we take random favorites for the 3 agents, you can see that the output, the aggregated pie chart, if you like, among the 3 categories always overshoots 100, except in cases like this. Okay, what can we do? It turns out we have some wiggle room here, because we can, to an extent, adjust the position of the red lines, the position of the phantoms. At the moment, the values are too high, but if we allowed ourselves to push the red lines a bit lower, closer to 0, the medians would go down, and so we would be closer to 100%. And in fact, if we sort of squish things far enough so that we go to exactly 100% in some, it turns out that that mechanism is still truthful. And we call that mechanism the independent markets mechanism, because it has an interpretation in terms of market clearing prices. And this is the kind of thing that happens then. So here we've pushed down the phantom lines far enough so that the numbers sum up to 100, right? And that looks good. In what sense is this fair? suppose two agents, agent 1 and agent 2, are all in for purple, and agent 3 is all in for green, right? It's 2/3 to 1/3, and then independent markets will exactly recover this proportional split. And that remains true if we put in additional voters. We call this type of mechanism a moving phantom mechanism, and there's a whole class of these with different properties. And these mechanisms might be useful in various different situations, both in participatory budgeting, but also, say, for deciding government spending, the priorities, what fraction should be spent on various departments, or maybe within charitable foundations that have various possible grantees, and they need to decide what are their priorities, what fraction of their spending should go to which causes. Now, these rules make sense when each voter gives you their ideal point, their most preferred budget, and they would like the actual budget split to be very close to what they think is optimal. But in many cases, this is not really what people want. Really, their thought process is something like this. I think this project is a good project, so a lot of money should be spent on it. So let's look at a different model, very simple one. So there are different projects, and you can either approve or disapprove each project, like we've seen. But here the projects can be flexibly funded, so they can take any amount. So the output is something like a pie chart, just a division of 100% among the projects. Here's an example with 5 agents and 4 projects, the blue, orange, green, and pink projects, and 3 different mechanisms for aggregating these approval votes. For example, agent 2 thinks that both blue and orange are good projects. So this agent is 100% happy with the utilitarian mechanism in this case. This person is 70% happy with the conditional utilitarian mechanism, and only 60% happy with the Nash mechanism. Okay, so what do these mechanisms, what do these rules do? Let's start with the utilitarian mechanism. It just picks the division of the budget that maximizes the sum of people's utilities. Right? So in this case, the sum of people's utilities with what it's chosen is 100%, 100%, 100%, 0%, 0%. And that turns out the highest you can do. In general, you can check that the utilitarian mechanism will always put 100% on the approval winners. That is the projects with the highest number of ticks. And in this example, blue got 3 ticks, whereas everyone else just got 2 ticks. Okay, so the utilitarian rule has some advantages. It's what's called Pareto efficient, so you can't make everyone better off. It's also strategy proof in this setting, because approval voting is strategy proof. You can check that you don't want to pretend that you like projects that you don't actually like, and the other way around, because that can only change the approval winners in ways that you don't like. But, very clear in this example, it's not a very fair rule, because agents 4 and 5 get 0% happiness. They are 40% of the population, so surely they should get 40% of the budget spent on things that they like. Okay, here comes the conditional utilitarian rule proposed by Duddy, which fixes this problem. What does this rule do? It splits the budget equally among the agents, so each agent gets 20% of the budget to decide what to do with. And they will spend their budget on something they like. But in order to be more efficient, they look at the other agents' approval sets and pick among the things that they approve the one that the most other people also approve. Okay, so agents 1, 2, and 3 have an easy time because they approve the approval winner, blue, so they spend all their money on blue. So this is why 60% of the money goes to blue. And now agents 4 and 5, what do? Well, they approve 2 things. They have equal approval score, so they split their money equally 10-10. So in total 20% to pink and 10% each to orange and green. So just as a sanity check, for example, if agent 4 decides not to like pink, then what happens now? Well, agent 4 spends the 20% on orange, right? And agent 5 approves green and pink, but green is more popular overall than pink, so agent 5 spends all his money on green. Okay, the conditional utilitarian mechanism is fair in the sense that each person gets their own chunk of the budget to decide what to do with, so no one is completely ignored. You can check it's still strategy proof, you want to say the truth, but unfortunately it is not efficient anymore. This example is an example of that. Suppose here we would put the 10% that's currently orange and make it blue, and the 10% that's currently green and make it pink simultaneously. Then I claim no one is worse off with that, right? Look at agent 2, right? The 10% from orange has gone to blue, equally happy as before. Similarly, agent 3 is as happy as before because while he loses 10% for green, he gains 10% from orange. And similarly, agent 4 and 5 are happy because 10% went to pink. On the other hand, agent 1 is strictly happier. Right? Agent 1 was previously 60% happy, and after the shift is 70% happy. So the conditional utilitarian rule is not efficient, but it is strategy proof and fair. Now the Nash rule is a little mysterious. It's named after John Nash, famous for the Nash equilibrium, but he's also famous for the Nash bargaining product. And this is the Nash product here. Rather, the utilitarian mechanism picks the budget division that maximizes the sum of utilities. Nash picks the budget division that maximizes the product of utilities. And that sounds weird at first, but if you think about it, it's actually a kind of neat idea. It's like taking the geometric mean of the utilities. And Nash will tend to want to equalize utilities, make everyone equally happy off, but will make people happier off if that's kind of cheap and a good deal. It's a good compromise between being egalitarian and being efficient. And so in this case, what does Nash do? Put 60% on blue and 40% on pink, and that makes kind of sense. So it rounds these first 3 agents to blue agents and the second 2 agents to pink agents. Okay, Nash turns out as fair. Why? Well, it won't make anyone completely unhappy. It will represent everyone a little bit, because if Nash makes someone completely unhappy, then they are utility 0, and so the overall product of utilities will be 0, and that won't be good for Nash. So it's fair. It's also efficient, one can check, so it's not possible to make everyone better off simultaneously, but it's manipulable. So now we've seen 3 different mechanisms, but none of them satisfies all 3 properties. None of them is efficient, strategy proof, and fair. Have we not found the best mechanism yet? No, it turns out that there exists no such mechanism. And it's actually relatively easy to see, so let me prove this impossibility theorem to you. Suppose agent 5 says this. Agent 5's true opinion is blue and pink are good. Now, what would an efficient mechanism do in this case? So first, let's notice that in this profile, orange and pink are kind of symmetric, right? In one ballot, they appear together, and they appear once with blue. So they are essentially similar, and so a good mechanism, a reasonable mechanism, will put the same fraction of money for orange and pink. Notice also that green is a bad choice in this example. It would be inefficient because if there was any money spent on green, it would be better to redirect it to blue. Everyone would be happier. Okay, so any efficient and symmetric mechanism needs to put the same amount of money on orange and pink and cannot put any money on green. And it also needs to put at least some money on both orange and pink, because if it spends no money, like the utilitarian mechanism, on orange and pink, then it's not fair to agent 4. Okay, so now look at agent 5. Given what we've said, agent 5 is definitely not completely happy. Right? Why? Because some money is spent on orange and agent 5 doesn't like orange. But now agent 5 can manipulate, can pretend not to like blue, but to like green. This is the profile we started out with. Well, what happens now? You can already see what we'll say is that the mechanism can only pick blue and pink in this situation, and therefore agent 5 in its true state is completely happy, and so this was a successful manipulation. Why is this? Well, we said before that you can't, if you want to be efficient, put money both on orange and green. But in this example, orange and green are symmetric, so you better put the same amount of money on them, but you can't put money on both, so you can't spend money on either. And by fairness, you need to spend money at least then on blue and on pink. And so we've seen that by manipulating agent 5 has become happier. So this is a little impossibility theorem, very easy proof. Turns out the same theorem was proved in 2005 by Bogomolnaya, Moulin and Stong, and then you did a very complicated proof, not just 5 projects but 17. It was very difficult. And here is a much easier proof. We're not geniuses, but rather this is a computer-found proof. We were very surprised when the computer spit out such a simple proof. I'll tell you later about the details of how this kind of approach works. So this is a computer-generated impossibility theorem. Interestingly, notice that we've used these symmetry arguments in the proof, and they are kind of not nice, so maybe there is a mechanism that satisfies all 3 properties if you don't require it to treat symmetric alternatives identically. But with the help of the computer, we can prove that you can actually prove this impossibility theorem without any symmetry arguments. But the resulting proof is very long. It doesn't take 1 step like here, but it takes 385 steps. And so it would have been difficult to find this by hand. So far we have looked at projects that can be flexibly scaled and can take an arbitrary amount of money, so that the budget can be thought of as a pie chart that you just have to divide in any way among projects. But in the city examples we've seen, projects are actually have a fixed price and can either be fully funded or not at all. So let's try to look at that in more detail. But let's make our lives easier and assume that everything costs the same amount of money. Say everything costs $1 to normalize, and we have K dollars available. That gets rid of this complication of very expensive projects versus very cheap projects. Okay, so now what we have to do is just elect K of the available projects, and that's the same thing as electing a parliament of K members. And that has been studied for centuries, and so let's look at what's around. Let's look at approval voting again. So each voter is allowed to approve as many candidates as they like. And Sweden actually in the 1890s thought about instituting such a system. And 2 mathematicians there proposed rules. Fragmen and Thiele proposed very interesting rules. And computer scientists have rediscovered them and picked them up in recent years and studied them. And the consensus in the field was that probably Thiele's method is better, but we've recently argued that Fragmen has some upsides that have not been recently appreciated. Let's have a look at an example to see what's going on. Here there are 6 voters, A, B, C, D, E, and F, and 18 candidates. And to read this figure, look at each column. So for example, voter A approves candidates 1, 2, 3, and 4. Voter D approves candidates 7, 8, 9, and 10. No one else approves any of the candidates that D approves. If you run Thiele's method on this, it does the following. It elects 1, 2, and 3, and then it elects 3 candidates that each of D, E, and F approves. So it gives each person, each of the 6 voters, exactly 3 representatives. And that's of course very fair. Everyone gets the same number of representatives. Now, but is it proportional? Does it give proportional representation? Maybe not. Namely, A, B, and C form 50% of the population. So of the 12 seats, they kind of deserve half, so 6 seats. And so maybe the proportional fair thing to do would be to elect 1, 2, and 3, but also 4, 5, and 6, and give voters D, E, and F only 2 representatives each. And that's what Fragmen does. And so now we see in this example there are 2 different possible choices. Both are fair in a certain sense, but not in another sense. And I think it's still left to future work to sort out these differences and decide which is more appropriate in what context. Now, both Fragmen and Thiele have one downside: they are manipulable. So neither of them are strategy proof. And so a natural question is, are there any fair proportional rules that are strategy proof? Now you could try to think hard to answer that question. The answer turns out to be no. Or you could look for computers to help you. And in particular, let's have a look at logic solvers or SAT solvers, satisfiability solvers. And an example where they can be useful is if you want to solve Sudoku. What you would do if you want to solve a Sudoku is you make variables, binary true-false variables, for each of the squares, and for each of the possible values of the squares 1 through 9. And then you add constraints to the problem that say that in each row you have to put each of the numbers 1 through 9 in that row, and that in at most one of the fields in that row can you put each number. And you do the same thing for columns and for boxes, and then you feed that problem into a SAT solver and it will tell you in milliseconds what the solution is to the Sudoku. Or it might tell you that it's unsatisfiable. That would mean that the hints are inconsistent. There's no way to fill out the Sudoku with the hints that respects the rules of the game. And if you think about it, designing a voting rule that's, say, fair and not manipulable is very similar to solving a Sudoku, right? Each possible input profile, each combination of preferences is a field. Some of the fields have hints in them because fairness tells you what kind of outcome is okay. And manipulability are constraints that connect different fields together. So let's try to use the same kind of solver to answer whether there exists fair and strategy-proof rules in our context. Here's a little Python program that does it. Let me talk you through it. So C is the set of candidates. Suppose we have 4 candidates, 3 voters, and want to elect 3 committee seats. So in the sense, each voter deserves one of the committee seats. Then we make a set of all the ballots. So that's all the subsets of C of any size. And then profiles are just combinations, one ballot for each voter. And the committees are just subsets of size K of the candidates. And then we initialize a satisfiability model where we make a new variable for each combination of a profile and a committee. And so this variable is going to be true if at that profile that committee is returned by the rule. Then we add constraints so that each profile at least one committee is returned and at most one committee, so exactly one committee is returned. And we add the hints. So we go through all the profiles and look and tell the solver that it's only allowed to return fair committees. And by fair, I mean something very minimal here. I mean that if one of the voters approves only one candidate, then because that voter deserves one of the seats, because there's the same number of seats as voters, then that candidate should be in the committee. Right. And then I implement strategy proofness, which just says that we go through each profile, each voter in the profile, and look through all possible lies they could tell. Every possible way that they could misrepresent that. And then we say it shouldn't be possible that once they've lied, they get a committee that they prefer to the previous committee. So the solution to this puzzle would be a voting rule that's strategy proof and fair. So let's try to solve this and give this to a solver. All right, so we ask Python to do this, and it encodes the problem and sends it to the solver, and the solver tells us it's unsatisfiable. Bam! We have an impossibility theorem. No such rule exists. It was pretty easy. Now the problem is other people might not believe us. There might be bugs in the code, for instance. This is not a proof. This is just a screenshot telling you it's unsatisfiable. But there's a nifty trick we can use. And this trick is called minimal unsatisfiable sets. We can look for a collection of the constraints we've put in, so in particular strategy proofness constraints and the fairness constraints, and we can ask a computer program to look for a small collection of these constraints that already lead to unsatisfiability. It's kind of a core, this is enough. And these voting problems tend to have very small, minimally unsatisfiable sets. So we can just give it to an MUS solver, a minimal unsatisfiable set, and it very quickly gives us a MUS with just 26 of the different constraints. Right? And these constraints, what do they look like? They are usually a pair between a profile and a manipulated profile. This kind of forms a graph. And if we like, we can inspect what this MUS solver has given us by drawing a graph. And in this case, that looks like this. Now, this is a pretty simple object. You have to do some detective work to understand what's going on. Each node here is a particular preference profile, and the edges connect different profiles and tell you that there might be a manipulation option. And if you stare at this long enough and put it in the right order, by doing some case analysis, you will get a contradiction, and this essentially encodes a proof that no fair committee rule can be strategy proof. And this kind of method has been used several times now to produce very difficult impossibility theorems that would have probably been out of reach of humans, and it's a very cool method. Now, the dissertation contains various other things. It also talks about private goods that you have to give to agents and they shouldn't envy each other. It talks about more applications of this SAT solver technique. But for now, I'll end it here. Thanks for listening. Bye-bye.